Okay, let us continue with this 4-bit binary adder. So in the last class we have considered this 4-bit binary adder, so which is having uh, two 4-bit numbers. So they have been used to generate the P's and G's, that is propagate and generate, and of course we have a Cin. So as we discussed in the previous class also, this is actually P0, this is G0, and this is P1 G1, and of course the remaining full adders are getting P's and G's, and of course you can see this is the Cin and this is the C out of the final thing. Of course we know that this is a ripple carry adder, meaning if you want to get the final output, so the carry has to propagate through the entire full adder section whatever we have, and finally the carry has to come out. We have seen in the previous video also, there is a possibility of having uh, a different configuration where you can able to bypass the carry, provided if all the bits, that is A's and B's, are such that it is used to propagate the carry. So if P0, P1, P2, P3 are equal to 1, then this select line will become 1. Once this select line becomes 1, so this is I0, I1. So since select line is 1 and this is I1, so whatever is your Cin will be bypassing the entire full adder section, and it will be available at the final carry out for further processing. So that's why this is called as carry bypass adder, or we'll also call it as carry skip adder. So in continuation with a similar type of full adder which is having a carry bypass, so this is hardly for 4 bits. So let us just move on to a 16-bit adder. So here it is 16-bit adder has been realized using 4-bit adders. So if you can see here, so this is bit 0 to bit 3 and then 4 to 7. Likewise we have 16 bits split into 4 different subsections. So each subsection has a setup. This actual setup is meant for getting the required value of what is that, G's and P's. So once we get the G's and P's, we can just move on and then try to get what is, whether it is carry has to bypass through this this carry propagation is actually uh, a section where it's going to pass through different stages. So now you can see we have a 4-bit binary adder which is being set up using a section of these blocks. This is setup, carry propagation, this is some generation, this is a mux. So this is exactly equivalent to this entire block is being represented over here. Let us see what is the time that is required to get the final output. So what we're considering, please have a look at this gray colored blocks. So assume that we are given all 16 two 16-bit inputs, that is A0 to A15 and B0 to B15. So they will going to actually give P0 to P15 and G0 to G15, which will be used for carry propagation. And of course we know that depending on the value of Cin and the values of P's and G's, the carry will going to propagate or not. So assume that here, okay, what we are considering in this particular case is, so this gray colored block, so this is the time that it is taking. So first it is the time taken by this setup block. So this setup block is nothing but purely consisting of AND gate and XOR gate to give the P and G outputs. So as we already know, let me just go back to this and show you. So this is how we are implementing this P's and G's. Okay, this is the implementation of G, this is the implement of P. So likewise we are going to get this is what is there in the setup. So in the setup I'm going to have this P0 to P15 and G0 to G15. So once we have that, let us consider this particular example. So of course let me just go back to that PPT and then okay, now if you can see here so here carry is propagating through this. So when does carry will propagate is whenever the select line is not equal to 1. So whenever select line is not equal to 1, the carry will certainly ripple through different 4 stages of your full adder. So assume that we have such type of input where it is rippling through this. So that's why it is flowing through this, and then let us assume that the subsequent 8 more bits are having such values of p's and g's, it will simply bypass that carry propagation. So this in this particular example, the time that is required for getting p's and g's is this t setup, and then you can see there is a m carry. So this values of m and n is nothing but, so the value of n is nothing but the number of bits. So actually here the value of n is actually 16, and that 16 is divided into 4 bits. So 16 divided by 4 is actually 4. So this m is actually 4 bit. So this is 4 bit binary adder. The entire thing is 16 bit binary adder, which is realized using 4 bit binary adders. And you can see here, this is T setup, that is time required to get the P's and G's. So of course we're going to get the P's and G's from all 4 different setup blocks simultaneously. So that's why we are not writing it 4, because it is only once you are getting it is T setup only once, and then M carry. So we are assuming that the carry is going to propagate through this. So that's what is here actually. T carry is the time required for one full adder to give the carry output. Since you have 4 such full adders, as we just mentioned here, so since you have 4 full adders, so it is actually M carry is now it's actually 4 T carry. Then you can see for an assumed combination of 16-bit inputs, it will bypass through this, it will bypass through this, and you can see whether it is bypassing through or flowing through this mux. You can see, is it not flowing through this mux? If you can see this gray color, gray color, gray color, actually the whatever carry you have, so if it has to come out of the final thing, so it is taking one, okay, because this tmux also takes some time. So that's what is if you actually find out what is the time of this one, so it's actually 16 by 4 minus 1. So it's actually 4 minus 1, which happens to be 3 T bypass. So if you can see this gray colored muxes, so this is 1 2 3. So time required for each of the mux to bypass that carry is actually, this is 3 T bypass. And then once we come to this 3 T bypass, I'm already over here. So once I'm over here, again here it is assumed that this will not going to bypass through this. Now it will again ripple through. So when it is rippling through, so now it is written as m minus 1. So because the last one, whenever it comes, so that is enough for you to get this t sum. The last one, what we're assuming is, okay, I'll just go to the example and then try to find out. It's actually if you have a 4-bit full adder, whatever that time required to get the output from a 4-bit full adder is actually m minus 1 t carry plus t sum. So t sum is the time that is required to give the final sum. So by this time, okay, these sums have been already out. It takes some extra time to get this t sum. So let us go to this example and try to find out how exactly these timings are calculated. Let me just take this example. Just assume that we have this, okay, 16 bit numbers of A. This is again 16 bit numbers of B. So, and of course this is Cin. So we have assumed this type of combination. If you can see here, this is actually 0 1, this is actually 0 0, this is 0 1. Just have a look at these G's. So G is nothing but A and B. So it is used to generate the carry, because in none of the combination of A and B, because not in any one of them it is not equal to 1, or both are not equal to 1. That's why all the G's are 0. Can you see, it's all the G's are 0. And then if we can carefully notice the P's, so wherever the A's and B's are dissimilar, now it is 0 1, it's actually 0 0, it is 0 1 1 0. Wherever it is dissimilar, you have a P is equal to 1. This is 1, here it is 0 because both are 0 0, here it is 1 1 1. So if you can see, this is the first 4 bit, this is the second 4 bit, this is the third 4 bit, this is the fourth 4 bit. As we saw in this block diagram also, so this is the one where it is propagating through this, meaning it is not bypassing through this. And the other one, what we have, the last one is also not bypassing through this. And whereas the intermediate two 4-bit adders, 4-bit adders are actually bypassing. So that is what is clearly shown here also. Can you see here it is the carry is rippling? So carry is rippling, that's why the time that is required to get the T carry over here is 4 T carry, and then plus 1 because there is a mux available. So whether the carry is coming through bypass or whether it is rippling through, it has to flow through one more T mux. You can see there is a time that is required to get the mux output. So your carry is there. Since if you can see here, since you have all p's as 111, this whatever carry that is there here will be bypassed to this point, because we have of course we have considered such type of inputs of a and b, so that all p's are 1. So this will going to certainly come down here. So one more tmux. So we are just simply concentrating on how does your carry is moving. And again you can see all p's are 1. So once the carry comes over here, it will bypasses all these things and then it will come through with one more tmux. If you can see here, this is setup time to get the values of p's and g's. After that 4t carry, that's what is my m carry, and you can see this is n minus 1, n by m minus 1, that is 3. Okay, this is bypass is nothing but tmux. So this is 1 2 3. So it is passing through 3 muxes, and you can see once you have your carry for your last 4 bit available, so as we saw in this case, so once the carry comes onto this stage, now it is again propagating through this. So propagating through this, so by the time it propagates to this one, so that's what is m minus 1 t carry, which is actually 3t carry. So by the time it comes down here, so now you can, of course you can certainly find it takes some time for your sum to get the output. So you have another t sum, because the last sum whatever that is required, because that here we are assuming the time required for generating the sum is equal to the time required for generating the carry. So that's why you're not writing 4t carry here, you're simply writing 3t carry plus 1 t sum. So this is the total time required by this adder to get a output voltage, provided these two conditions, provided here it is not bypassing, here also it is not bypassing, whereas it is bypassing through these two things. Suppose if you consider a different combination where it bypasses this, where it is passes through this, then you can certainly take out this 4t carry, you can certainly take out this another 3t carry, then this timing will be slightly different. So timing will be totally different. This is the time that is given with an assumption that we are having this rippling through the first set of m bits and then last set of m bits. So that's why you have this mt carry and m minus 1 t carry. Suppose if all of them are bypassing, you will end up with this will be bypass, and of course this will not be there, this will also be not there. So likewise, of course it slightly changes depending on the type of input you have. So this is one of the worst possible combination you can think of. Okay, this is how you can able to get the output from or the time required for generating the total sum output from a 16-bit adder. If you can see here, the time required for generating the final output using ripple adder and bypass adder. Suppose if the value of number of bits are lesser, then ripple carry or ripple adder would be a best performer, because this bypass adder will going to have a few few extra timings in terms of making the setup and all those things, whereas in case of ripple adder, so you're not supposed to generate any p's and g's, so it is simply the a's and b's are used to get the values of sum and carry out. So as long as the number of bits are less than 4, you can certainly go with the ripple adder. As the value of number of bits for addition becomes more and more, you can see the bypass adder is a better performer compared to the ripple adder. Suppose if you don't have these type of bypass adder, suppose if you use such type of 16-bit 16 full adders, then naturally it will take longer time. So that's what is depicted here. As the value of n increases, if you are going with exclusively ripple adder, then it takes longer time. If you go with the bypass adder, so of course with segregation of entire 16 bit into 4 different 4-bit binary adders with this carry bypass configuration. It will going to have a reduced output, reduced time. Okay, here this is another type of architecture for reducing again the time required to get the output, the entire sum and the carry output. If you can see here in the previous case, so whenever a carry has to propagate through this, before we get the sum output, of course, as we saw in this particular case also, assume that when I'm here, so whenever a value of 1 comes, so my sum is different. Suppose if the value of carry in is 0, the sum is different. So because we know that sum is depending on, so we know that what is sum. So sum is actually given by P exclusive Cin. If the value of Cin differs, then my entire sum value changes. So what we are doing in another configuration is, so it's actually we are predicting, if you can see here, if the value of carry in is 0, you predict what is the carry vector. If the carry in is equal to 1 with the known values of P, you predict what is the carry vector. So since you are predicting the value of carry vector with the value of Cin as either 1 or 0, it's already ready. So since it is already ready, so once the actual value of Cin comes, instead of rippling through those 4 bits, you simply take this 4-bit whatever already generated carry vector you have, you simply output this onto this so that your sum can be easily generated. So instead of waiting for the carry to ripple through 4 different adders, once the value of Cin comes, we are actually predicting the values of Cin whenever the value of Cin is either 0 or 1. If it is 0, you have a different set of carry in. If you have the carry in as 1, you have a different set of vector. So as soon as the actual value of carry in comes, if it is 0, you select this and put it as your carry vector to generate the sum, because it doesn't require a time to ripple because it's already available here. And then if it is 1, you take this particular carry output which is already being calculated prior to this actual coming, because you already predicted the carry vector that is required when the actual carry in is 1. So that way we can able to certainly reduce the time that is required to generate the sum, because you are already selecting the carry before it comes. So before it comes, you are already predicting it. So once it comes, you select either this or this. So these type of carry select adders are also used in realizing these 16-bit adders. You can see this is how it happens. So you have with carry as 0, you are predicting; with carry as 1, you are predicting. When the actual carry comes, so it is being used for your sum generation. You can see the time that is required for getting the adder is the T setup. So T setup is actually the time that is required to get the output from this what A0 and B0, sorry, G's and P's, and of course the, because this is also a logic which is implemented using gates. So if the value of 0, but if the value of Cin is equal to 0, you won't have a set of carry vector. If it is 1, you won't have a set of carry vector. So all those things are there accumulated in this T setup. Of course, you can see n by mt carry, the time required for carry to be generated. And of course, you can see this mux will going to propagate through these 4 different muxes, and then the final T sum. So this is the overall time that is required to generate the carry, just looking at this gray colored path. So this is the time setup, and then okay, n by mt carry, and then we have this m tmux. So because you have 4 such tmux, again the value of n is the total number of bits, and m is okay how many sub blocks you have. Here it is 16 and this is 4. Of course we have 4 different muxes, and finally it takes some time to get the sum output. So this way we can able to implement carry select adder. So this is one such critical path. Okay, next we shall have a look at one more type of configuration, which is carry look ahead adders. So we'll just have a look at this in the next video.